So let's finish up symmetric, alternating, and dihedral groups. I think when I left off on the last video, I said we do dihedral groups next. Actually, we're going to do alternating groups next, and we'll wrap it up with dihedral groups. So we know from the previous result that every element of S sub n can be written only as either an even number of transpositions or an odd number of transpositions. So what we're going to do in Theorem 1.6.8 is define the alternating group by letting n be greater than or equal to 2 and let A sub n be the set of all even permutations of S sub n. That is, permutations that can be written as an even number, a product of an even number of transpositions. The claim is A sub n is a normal subgroup of S sub n of index 2. So it's half the size of S sub n. The cardinality of S sub n over 2, n factorial over 2 is the order of A sub n. Furthermore, A sub n is the only subgroup of S sub n of index 2. And this group is called the alternating group on n letters, familiar to you from senior level algebra. Okay, so a handful of claims here. Let's go to the proof. Claims being normal subgroup of S sub n, index 2, and only subgroup of S sub n of index 2. All right, so what we'll do is first introduce a little group C, multiplicative group on the symbols -1 and 1. So it's isomorphic to Z2, but the binary operation is multiplication. But anyhow, it's a group of order 2. Identity is 1. The other element's -1. It's its own inverse under multiplication. And then we're going to map F, mapping F from S sub n into this group C, defining F of sigma to be the sign of sigma. Remember, the sign of a permutation in S sub n was 1 if the permutation was even and -1 if the permutation was odd. And we claim this is an epimorphism. This is an onto homomorphism. So take a couple of elements, sigma and tau, from S sub n. If sigma and tau are both even or both odd, then the product is even. We'd have even number of transpositions, even number of transpositions. Product would be even number plus even number, which is even number of transpositions. Similarly, if they're both odd, we've got odd plus odd is even. So that's the claim there. Similarly, for maybe sigma even and tau odd, or the other way around, then the product is odd. So we got 4 cases there. And in each case, what we have is that F of sigma tau equals F of sigma, F of tau. For example, if we had sigma and tau are both odd. If sigma and tau are both odd, F of sigma is -1, F of tau is -1, sigma tau itself is even, so F of sigma tau is +1. So we get +1 equals -1 times -1. It's just a matter of checking those 4 cases. So we actually do have a homomorphism because we've got this behavior here. F is onto, that's easy enough. Let's look at, we've got n is at least 2. So consider the mapping of the transposition 1, 2. That's definitely in S sub n when n is at least 2. That's an odd permutation, so that's mapped to -1. The identity, say writing it as a product of 2 transpositions, the identity is even, recall, and so we get the 1 out. Yeah, it's onto, and so we do have an onto homomorphism, a surjective homomorphism that is an epimorphism. Okay, so we're going for normal subgroup. All right, we have a homomorphism. The kernel of that homomorphism would be everything mapped to the identity of this group C. Group C only has 2 elements. It's a multiplicative group. The identity element is 1. So the kernel of F would be those permutations in S sub n mapped to 1. That is, those permutations in S sub n that have a sign 1, SGN sign 1. That is, the permutations in S sub n that are even. That is, the kernel is just this A sub n stuff. Now, we know kernels are subgroups, first off. Secondly, theorem 1.5.5, rather recent one, tells you that the kernel of a homomorphism is in fact a normal subgroup. So we do have that A sub n is a normal subgroup of S sub n. That takes care of the normal subgroup claim. We've still got the index claim. The first isomorphism theorem tells us if we take a group, mod the kernel of a homomorphism, that quotient group is isomorphic to the image of the homomorphism. First isomorphism theorem. Told you we'd use that one a little bit more than the others. Well, the kernel of F, we just argued, was A sub n. So what we've got is S sub n mod A sub n is isomorphic. Whoops. Is isomorphic to the image of F, was an onto mapping. The image was that entire group C. So the cardinality of this group is the same as the cardinality of this group to which it's isomorphic, when C only has 2 elements in it. So it must be S sub n mod kernel of F only has 2 elements in it. That is, there's 2 cosets there. And the index of A sub n and S sub n must equal 2. Lagrange's theorem says when the index is 2, you've got a subgroup of order half the size of the original group with finite groups. Lagrange's theorem is kind of clean. So we get the order is n factorial over 2, half the size of the symmetric group as claimed. The additional claim, A sub n is the only subgroup of S sub n of index 2. That we're going to leave as exercise 1.6.6. Back to the notes. And so we have a new group. We have the new collection of groups. We have the alternating groups. We're shifting gears here, talking about simple groups now, something that'll be explored in a good deal more detail later. For now, simple groups are a convenient thing to talk about in connection with alternating groups, because it turns out the alternating groups are simple with one exception. So minimal motivation maybe to look at this definition at this stage. But definition 1.6.9 says a group G is simple if G has no proper normal subgroups. No proper normal subgroups. Trivially and vacuously, G itself is a normal subgroup of G, and the identity, the group of order 1, is a normal subgroup of G itself. So not those. So we're saying a group is simple if there are no normal subgroups other than the trivial one, or the trivial ones arguably, G itself and the identity group. Now you needed normal subgroups to make quotient groups. So we can make interesting quotient groups out of simple groups. They are, in some sense, choose my words carefully. I want to say they're kind of like they're indecomposable. We can't make quotient groups out of them. There's some sense in which we can't break them into smaller pieces. You can't make quotient groups with simple groups other than in a trivial way because they have no proper normal subgroups. Why this is important, we'll elaborate on in the not too distant future. It should appear in around the end, but hopefully in Algebra 1. First, an observation about simple groups. Any proper subgroup of an abelian group is normal. For abelian groups, all subgroups are normal. So the only way we could have a finite abelian group would be to have a group with no proper subgroups. So take the integers mod p, where p is prime. No proper subgroups, consider Lagrange's theorem maybe. And So simple groups. So here's some examples of simple groups, uninteresting ones. They're vacuously simple. They have no proper normal subgroups because they have no proper subgroups. So of course they're simple because of that reason. The story on the study of finite simple groups is kind of a long story. The study is fundamental to the study of finite groups because, in a sense, it's a nice disclaimer, all finite groups are composed of finite simple groups. Now, how this composition works is pretty subtle. It's more every finite group is associated with a unique collection of finite simple groups. The result that elaborates all the details on that is called a Jordan-Helder theorem. It appears at the end of chapter 2 in section 2.8 in the Hungerford book. The classification of finite simple groups was a program from sometime in the 1950s through, it was kind of pretty much wrapped up sometime in the 1980s. So it spreads over some 3 decades. So this was the problem in abstract algebra throughout the 60s and 70s and piece of the 50s and piece of the 80s. I have some notes from Introduction to Modern Algebra that describes a little bit of the history of this and actually gives a classification result for the finite simple groups. But there's reasons to look at these kinds of groups. In fact, alternating groups give examples of simple groups. In the next theorem, we'll see that the alternating group A sub n is simple if and only if n doesn't equal 4. So all but 1 are simple. This is given as an exercise in the Fraley book for the senior level class. I have a supplement out there that goes through Fraley's proof that for n greater than or equal to 5, alternating group A sub n is simple. It's basically the same proof we're going to go through here. So we will state as theorem 1.6.10, the alternating group A sub n is simple if and only if n is not equal to 4. To prove this, we need a couple of lemmas. So we'll state 2 lemmas. Both of them concern 3 cycles. So 3 cycles are going to play a big role in the 2 lemmas and in the proof of theorem 6.10. And this is not so hard to follow. The theorem itself will have 5 cases, and we'll go through and kind of beat those cases to death in terms of cycles. You know, every permutation can be uniquely decomposed into a product of disjoint cycles. So this product of disjoint cycles will pop up again and again. Okay, so well, let's hit these results then, starting with lemma 611, which states, let R and S be distinct elements of the set 1 through n. The claim is A sub n greater than or equal to 3, is generated by the 3 cycles R, S, and K, such that K is between 1 and n and is different from R and S. Okay, so a little elaboration on what's being said. You're given R and S. So these come to you as given distinct elements of 1 through n. And then for those 2 given elements, you're taking those in a first and second position in a 3 cycle, and you're taking all 3 cycles that have R as their first element, S as their second element. Of course, those can be cycled around for different representations of that 3 cycle. And the third element ranges over all other possible values for the symbols to keep these distinct, right? It can be anything between 1 and n. You don't repeat the R and the S. So claim is this collection of 3 cycles generates A sub n. Okay, a little case, n equals 3. The set of 3 cycles are, without loss of generality, say 1, 2, 3, along with that squared, which gives us 1, 3, 2, that cubed, which gives us the identity. This gives us 1, to 3 elements. So these are the 3 elements of A sub 3. This is certainly an even permutation. The identity is an even permutation. Are 3 cycles even permutations? Yeah, they're products of 2 transpositions. Let's maybe jump ahead just a little bit to this statement here. Here we've got a cycle, ACB, and that 3 cycle can be written as a transposition AB times transposition AC. A is mapped to C as required. B is mapped to A as required, and C is mapped to A and then to B. So C is mapped to B as required. So yeah, returning back up here, this 3 cycle, that's even. 3 cycles are even because of this observation here. So both of these 3 cycles are even. So that takes care of, that additional observation takes care of the case when n equals 3. When n is greater than 3, A sub n consists of all even permutations. So A sub n is generated by all pairs of transpositions, either of the form A, B, C, D, disjoint transpositions, or A, D, A, C, transpositions that share 1 element. So we're talking about a product of an even number of transpositions. So we're looking at what you could have for pairs of transpositions. You take 2 transpositions, either they're disjoint or they share a single element. If they share 2 elements, they're going to multiply together to give you the identity, and we don't need those. So the claim here is A sub n, consisting of all even permutations, is generated by the set of all pairs of transpositions of the form AB, CD, or AD, AC, of that form. I'm not fixing any symbols in this part of the conversation. So if we take AB, CD, those 2 transpositions, that permutation is equivalent to the product of these 2 3 cycles. So we're shifting gears here and trying to talk about 3 cycles now. Let's confirm that. There are going to be a bunch of claims about products of permutations in this, and I don't want to go through all of it in detail. It has been very thoroughly double-checked, so there's no typos in the little cycle products that are presented. But let's check this one. We want to show A is mapped to B. Let's see, A is mapped to C, and then C is mapped to B. So yeah, A is mapped to B. B, reading from right to left, B is mapped to A. B is mapped to A, so that closes off this little cycle, this transposition. C is mapped to D. Let's check that. C is mapped to D here, and that's the conclusion. So yes, C is mapped to D. Is D mapped to C? D is mapped to A first, and then A is mapped to C, though that, yeah, D is mapped back to C. Similarly, we explored this just a second ago, we can take this type of product of pair of transpositions, and that produces a 3 cycle. So what we're getting, maybe is we want to read these from right to left as well. We know that if I take everything of this form on the left-hand side, along with everything of this form on the left-hand side, that's a collection of permutations that will generate A sub n. That's all possible, non-trivial, non-identity. Products of pairs of transpositions. Well, it turns out this kind of product of a pair of transpositions can be written as a product of a pair of 3 cycles. This type of product of a pair of transpositions is a 3 cycle. So we're making an observation here that if we take, instead of the stuff on the left, those kinds of products of pairs of transpositions, the stuff on the right, which involves 3 cycles, if we take the set of all 3 cycles, that generates all pairs of such transpositions, this type, and so generates all of A sub n, because the transpositions of this type and this type generate A sub n. So we could say all 3 cycles of these forms generate A sub n. That's not what we're trying to show. Up here, it says we're dealing with a situation here where we have a particular collection of 3 cycles. We always have the first and second positions the same, written in this order. And that's not what we have necessarily down here. We've just got some 3 cycles. Okay, so given distinct, let's see, recall that we're started with a given distinct R and S. Yeah, R and S are given. So let A, B, and C be distinct elements from R and S, distinct from each other and from R and S. Then any 3 cycle of A sub n has to fall into one of the following categories. And we'll deal with this various cases throughout the proof of this theorem 10 ultimately. We get a 3 cycle of the form RSA or RAS. This is a 3 cycle that contains both R and S, and it sends R to S and S to R. We could have 3 cycles that contain R only and don't contain S, contain S only and don't contain R, or contain neither R nor S. So we've got these 5 kinds of 3 cycles as related to a given R and S, and whether the 3 cycles contain both, one, or neither of R and S. All right. We're going to write each of those 5 types of 3 cycles in the form RS something, RSK, a product of 3 cycles that are of the form RSK. All right, excuse me. First type, RSA. Well, that is the type, element R, given element R, given element S, and some K. K equals A in this case. RAS, given element R, given element S. Take element A and square it. Indeed, if you square this permutation, you'll get that permutation. Let's maybe check the last one since it looks like the most difficult one. Third type was R and A and B. We can write that as RSB times RSA squared. The pattern here again is we got an R first and an S second on the right-hand side in all of these little 3 cycles. SAB, the fourth type, can be written as RSB squared, RSA. And ABC, which doesn't involve any of the R's, can be written, or any of the S's, can be written as RSA squared, RSC, RSB squared, RSA. All right, I'd call this a computational proof. Let's do the computation on this last one and make sure that's right. So is A really mapped to B? Let's see. A is mapped to R first. Then R is mapped to S. Then this permutation applies again, in which case S is mapped to B. No B's there. No B's there. Let's try that again, sorry. I'm trying to show R is fixed. R is mapped to S. Oh, I read the second one wrong. R is mapped to S, then S is mapped to B, then B is mapped to R, then R is mapped to S, then S is mapped to A, this is squared, and then A is mapped to R, so that, yeah, there we go, R is fixed. So R doesn't appear on the left-hand side. Let's check S as well. S should be fixed. S is mapped to A, no A's, no A's. A is then mapped to R is then mapped to S, so that S is mapped to S, it's fixed, and it doesn't appear on the left-hand side. The standard with a notation is to not show the fixed points. So R and S are fixed. They disappeared from the conversation. I'd introduce them to the conversation because this is our agenda. And let's see if A is mapped to B, is mapped to C, is mapped to A. A is mapped to R, then to S, then to B. No B's. A is mapped to B as needed. Let's see where B is mapped. It better be C. B is mapped to R and then S because of the squaring. S is then mapped to C. No, C is over here. B is mapped to C. Finally, is C mapped back to A? C. C is mapped to R. R is then mapped to S squared and then to A. Yeah, C is mapped back to A, and indeed, that's what you get. So that's the most difficult one. And it's straightforward to check all these computations. So, given R and S, any 3 cycle in A sub n, all the 3 cycles are even, so they're all in A sub n. Any 3 cycle must be of one of these 5 forms. And any of the 3 cycles can be written like this. Can be written for the given R and S as a product of R, S, something. There's explicitly how to do it right there. All right. We saw that all 3 cycles generate A sub n. That was our first observation. So when we looked at the pairs of transpositions, and we showed that the 2 kinds of pairs of transpositions can be written as products of 3 cycles. So if we had all 3 cycles, then we could generate A sub n. Here we've shown if we only have 3 cycles of this sort for given R and S, then we can generate all 3 cycles, so we can generate A sub n with that as well, and that's the proof of that. So these kinds of 3 cycles generate the alternating group A sub n. All right, lemma 1.6.12, so a second lemma. This one we'll get a lot of mileage out of in the next section. Says if n is a normal subgroup of A sub n, n greater than or equal to 3, and n contains a 3 cycle, then n equals all of A sub n. Excellent. So we're trying to ultimately show a lot of the A sub n's are simple. That is, if we take normal subgroups of those A sub n's, then they either equal the trivial group, they don't here because it contains a 3 cycle, or they equal the whole group A sub n itself. So if we can show that normal subgroups contain 3 cycles, then we're in business to use this result here and say that normal subgroup is not a proper subgroup. So that's why we're looking at this. Let's see what happens. Okay, let R, S, and C be distinct, where R, S, C is this 3 cycle in this hypothesized to be normal subgroup of A sub n. So n's hypothesized as normal subgroup and containing, say, this 3 cycle. So take a K different from R, S, and C. The 3 cycle R, S, K is an N since, okay, so we've taken a 3 cycle where we've fixed the first element and the second element the same as this given element. And we've chosen a third element to be something different, right? You can see where we're trying to use that lemma 1.6.11 thing. And we can take this RSK and write it as RSCK, RSC squared, CK, RS. Straightforward to check the computation, but where are we going here? Here's where we're going here. We've said RSC is a 3 cycle in N. Okay, then that 3 cycle squared is also in N because it's a group, so closure under the binary operation. We've multiplied on the left by this product of transpositions and on the right by this product of transpositions. Let's bracket those off. So on the left, we've multiplied by this thing here. By the way, that's a product of 2 transpositions, whatever it is. It's an even permutation. It's an element of A sub n. And on the right, we've multiplied by the inverse of that. Right? We've got RSCK RSCK times CKRS. These are inverses of each other because we've got distinctness. This was set up where all the symbols are distinct: the C's, the K, the R, and the S. Reversing the order doesn't really matter, but it doesn't hurt. We do have commutativity when we deal with disjoint permutations. That'll play a role here shortly. But what this product representing this 3-cycle is an element of A sub n times an element of n times an element of A sub n inverted. Well, that's sort of an A inverse style product. And we know if we have a normal subgroup that we get A capital N A inverse to be a subset of capital N. Theorem 1.5.1 part 4, part of the definition of a normal subgroup. So it's right here we're using the normality. We've got an element of n. Actually, we started with this element of n and then used the square of that element. It's still an element of n, multiplied on the left by an element of A sub n, and on the right by the inverse of that element. If we can show we have a normal subgroup, we hypothesize that, then this thing here must be an n itself. So for given R and S, given as the first two elements of the 3-cycle, we hypothesize to be an n. It's actually not R and S that are in n, it's this 3-cycle that we get in n. So given this R, S, and C, we have all cycles of the form R, S, K in n, as we just showed, given the R and the S, where the K has to be chosen to be distinct from the R and S. Well, if you've got all R, S, K for a given R and a given S, K, where K can range over all the other possible values of the symbols, lemma 1.6.11 tells you these 3 cycles generate A sub n. We've shown that n contains all cycles of this form. If it contains all cycles of this form, because we're building them out of this cycle in the definition of normality, if it contains all cycles of this form, where K ranges over the symbols other than R and S, then lemma 16.11 tells you that collection of 3 cycles generates A sub n. We've got that collection of 3 cycles in capital N. We must have that capital N actually equals A sub n, because those 3 cycles alone generate A sub n. Big punchline: if n contains any 3-cycle and n is a normal subgroup of A sub n, then n equals A sub n. Again, the normality was used right here. It's kind of subtle, but that's where the normality was used. If a normal subgroup contains any 3-cycle, then it must equal A sub n. Okay, here comes cases. I'm going to go crank through 5 cases. This will be computational. We'll check at the end and make sure we really covered all 5 of the cases, or all 5 of the cases covers everything possible. So I might present the last part a little bit different from my standard way. The claim is the alternating group A sub n is simple if and only if n doesn't equal 4. Okay, let's take care of some little stuff here. If A2 equals 1, or A3, or sorry, the cardinal, if we consider A sub 2, we're looking at a group of order 1. If we consider A sub 3, we're looking at a group of order 3. These don't have subgroups, so these are simple. I mean, they're isomorphic to the trivial group and Z3. No subgroups, so vacuously those are simple. 4, when we look at n equals 4, A sub 4, it's to be shown in one of the exercises, 1.6.7, that if you'll take the identity along with this product of 2 transpositions, it's even, so it's something in A sub n, this product of 2 transpositions and this product of 2 transpositions, this actually is a normal subgroup of A sub 4. Proper normal subgroup. It's only got 1, 2, 3. It's got 4 things in it, and A sub 4 is of order what? 4 factorial over 2. Order 12. So here you have a subgroup of order 4 and a group of order 12. And it's a normal subgroup as to be shown in the exercise. So it's just checking details. So 4 stands out as an oddball case. There's some comments about this in some of the supplements I have for this senior level algebra class. So on to n greater than or equal to 5. So that takes care of the little cases. Now we'll consider, working under the umbrella assumption without loss of generality, that n is greater than or equal to 5 now. We'll show that if n is a non-trivial normal subgroup of a sub n, then n equals a sub n. In other words, a sub n has no non-trivial proper normal subgroups. The only non-trivial normal subgroups are a sub n itself, and that's not a proper normal subgroup. So a sub n is simple. We'll do this in 5 cases, and we'll check at the end to make sure these 5 cases really cover everything possible. And there's going to be a lot of conversations about 3 cycles and a little bit of a conversation about, I think we'll do a 4-cycle or longer length cycle at one point. Case 1, suppose n contains a 3-cycle. Well, we just showed in that lemma, if we have a normal subgroup that contains a 3-cycle, it has to equal a sub n. So case 1 is really what we did in the previous lemma. So that takes care of n contains a 3-cycle. Now we only need to consider the situation where n doesn't contain a 3-cycle. Case 2, n contains an element sigma, which, when written as a product of disjoint cycles, I told you we'd be writing permutations as products of disjoint cycles a lot. I guess it's theorem 1.6.3 that lets us write every permutation as a product of disjoint cycles. Written as a product of disjoint cycles, has at least one of the cycles of length greater than or equal to 3. I'm sorry, greater than or equal to 4. So that is, sigma is a cycle of length r, where r is greater than or equal to 4, times some tau. To take this as a disjoint, writing sigma as a disjoint product of cycles. Here's one cycle. Well, tau itself may consist of several cycles, but anyhow, make tau disjoint from the R cycle, A1 through A sub R, can be done. Again, we can write things as disjoint cycles. A1, A2, A3, that's a 3-cycle. All 3 cycles are in the alternating group. Right, we've got 2 things going on here. There's 2 moving parts. There's the big alternating group. That's the umbrella group in this conversation. So everything happens in A sub n. Capital N itself is a subgroup of A sub n. So if we take A1, A2, A3 as an element of A sub n, 3 cycles are even permutations. So that 3-cycle is in A sub n. It consists of all even permutations. Call it delta to have a symbol for it. Sigma, this permutation, we've hypothesized to be in n. Sigma is in n. N itself is hypothesized to be a normal subgroup. Sigma inverse is in n simply because sigma is, and since n is normal, if we take that given sigma and conjugate it on the left and right by delta, that'll give us something in n as well. Sigma is in n right here. We've taken an element of A sub n. We've conjugated that sigma, an element of n. Since n is a normal subgroup, this conjugation will be in n as well. Theorem 1.5.4, part 4. If that looks weird to you, you might want to pause the video and read what that one says. It says something of the form, A capital N, A inverse, is a subset of capital N. And that's what we're using here. This idea is going to play a big role in the computations in these remaining cases. So because of the normality, we get delta sigma, delta inverse to be in n. That's in n, sigma inverse is in n. So let's multiply that conjugation there on the left by sigma inverse. And that'll be something in n. All right. We can write this sigma inverse delta sigma delta inverse thing in terms of the symbols we've introduced is this. So let's see, we got a sigma inverse, that's inverting this element. That'll give us tau inverse times the inverse of the cycle. Just write the cycle down in the reverse order. That's what we have here, started at a sub 1 and cycle through them in the reverse order. We've started at a sub 1 and the way this is written up. Doesn't matter where you start a cycle. There's not a unique representation of those. But this is the inverse of that cycle, so we've done the inverse element thing correctly. Delta, sigma, delta inverse. Write this down in the reverse order as well. We started at a sub 1. So that's just substitution, nothing to check there. Hey, remember how the tau was chosen to be disjoint from the symbols A1 through A sub r? Then I can slide this tau around left and right across these cycles that only involve A1 through A sub r, because tau doesn't involve those symbols. So we get some commutivity with the taus. We can move the tau over here to the tau inverse or vice versa, move the tau inverse over here to the tau, and ignore those. The tau and the tau inverse compose to give the identity. You may commute the taus with these other things because of the disjointness. So we've lost the taus. Now it's a matter of going through, multiplying these things together and showing that that produces a 3-cycle A1, A3, A sub r. Let's check a piece of that. Let's see if A sub r really is mapped to A sub 1. I think that's, if any of them are interesting, that's the interesting one. It must be a bunch of stuff is fixed, which makes sense. Hey, look, this cycle has as its inverse this cycle. Okay, A1, A2, A3, those are going to get in the way here. And there's this additional term down here. But if we stay away from A1, A2, A3, looks like we're largely going to get a lot of fixed points. So that's the reason there's so few terms written down here. But let's check the A sub r. A sub r, let's see, reading right to left. I start down here. There is no A sub r. Go to the next one. A sub r is mapped to A sub 1. A sub 1 is mapped to A sub 2. A sub 2 is then mapped to A sub 1. So indeed, A sub r is mapped to A sub 1 as required. The A1s and the A3s and the other stuff, it all satisfies the claimed conditions. And let's start taking some of those computations as given. So what we've shown is that N contains this 3-cycle, A1, A3, A sub r. R is not 1 or 3, is it? Remember, R was greater than or equal to 4, so there's where that's being used. So we've actually shown that this thing here is an N, this thing here equals this 3-cycle. There's a 3-cycle in capital N, but lemma 6.12 tells you if you have a normal subgroup of A sub N that contains a 3-cycle, then it must actually equal A sub N. All right, so let's see. The first one involved a cycle of length 3. The second one involves cycles of length at least 4. So let's see what else we get. N contains an element sigma, which is a product of disjoint cycles, at least 2 of which have length 3. Okay, I think the first case had exactly 1 cycle of length 3. Yeah, that's right, because it used the previous lemma. So here we've got a permutation that consists of at least 2 cycles of length 3. Say that permutation sigma is this 3-cycle times that 3-cycle times whatever other stuff. So in its cyclic decomposition, it has 2 3-cycles and some other stuff. So take the tau to be disjoint from the symbols A1 through A sub 6. So this is simply what sigma is. Tau is what sigma does to the other symbols. A1, A2, A4, that's in A sub N, right? We're going back to the big group. First, we had a conversation about sigma in capital N. Now we're going to the big umbrella group, the alternating group, A sub N. This 3-cycle is in A sub N, right? 3 cycles are in A sub N. In other words, 3 cycles are even permutations. Yeah. A 3-cycle can be written as a product of 2 transpositions. It's one of the first things we did today. So this 3 cycle being an even permutation is an A sub n. Call it delta. All right, as we had previously, if we'll take sigma inverse, delta, sigma, delta inverse, then we get this 5 cycle. It's the same argument. The tau inverse and the tau cancel. We substitute it in. Normality was used, and all of this is based on the fact that capital N is normal. The normality was used in establishing that this thing here is an N. So N contains this element. That's the details in case 2 that we've glossed over here. So now we've got that capital N contains a 5 cycle. But hey, in case 2, we showed if capital N contains a cycle of length 4 or greater, then N equals A sub N. This one contains a 5 cycle. Well then, as in case 2, N equals A sub N. So single 3 cycle, case 1. 2 or more 3 cycles, I mean, tau could contain some 3 cycles for all I know, but 2 or more 3 cycles, case 3. So I think we're down to, a single 3 cycle and transposition. There's something we haven't covered. Let N contain an element sigma, which is the product of 1 3 cycle and a bunch of 2 cycles. Say sigma equals A1, A2, A3 is a 3 cycle times some tau, where tau is disjoint from the 3 cycle and tau is a product of itself disjoint 2 cycles. So the longest cycle we have is a 3 cycle. All the other cycles are 2 cycles. Then sigma squared, taking this to be sigma. Sigma squared is an element of N because sigma is an element of N. Sigma squared, it's a slightly different argument here, can be written as A1, A2, A3 times tau, A1, A2, A3 times tau, was simply replacing what we have here. The taus get together again. Now we've got tau squared, which is the identity. This time, because remember tau was a disjoint collection. Here it is, disjoint collection of 2 cycles. So every 2 cycle present in tau is present a second time in tau squared, and we've got the disjointness of the 2 cycles. We can permute things around. So the 2 cycles get together and switch back, as it were. So this is called an involution because tau squared equals the identity. So tau squared disappears from the conversation. The disjointness is used along with the fact that tau consists of a bunch of disjoint 2 cycles. That leaves us with A1, A2, A3 squared, little typo there, it should just be a squared. Square 3 cycle, you get the 3 cycle back, but little error there, that should be an exponent of 2. So N contains this thing, N contains a 3 cycle. If N contains a 3 cycle, lemma 1.6.12 tells you N equals A sub N. One last case. So here we're taking every element of N is the product of an even number of disjoint 2 cycles. So we're taking the elements of N. We know they are elements of S sub N. So we know they have unique cycle decompositions, and all of this is based on the unique cycle decompositions. So let sigma be an N, where sigma is a product of these 2 disjoint transpositions times some tau. So tau is a bunch more disjoint transpositions. Each transposition is tau, and tau is disjoint from the others as well as these 2. That's what we're getting at here. So we've written sigma as a product of disjoint transpositions. Not every permutation can be written as a disjoint product of transpositions, but that's our setting here. Right? I'm not saying every every permutation can be written like this, but here we're going through all these cases and this is what we're left with. We'll check that here in a little while. Then A1, A2, A3, that's an element of A sub n, right, 3 cycles are even permutations. We're going back to the big umbrella group, A sub n. So to note that transposition as delta, sorry, that 3 cycle is delta, that element of A sub n. And as we had in case 2, this is where normality is used, we'll find that sigma inverse, delta sigma, delta inverse is in n. When we compute that, substitute in, tau inverse and tau, they get together again, as has happened before. And if we'll perform the multiplication here, I am getting kind of tired of that, we get A1, A3 as a transposition times A2, A4 as a transposition. But we're not quite done this time. Knowing I get a product of 2 transpositions in n doesn't help a whole lot. But remember, we're considering now, without loss of generality, n greater than or equal to 5. We took care of the little cases kind of on the side at the beginning. Since n is greater than or equal to 5, there's another element that's not in either of these transpositions. Let's call that other element B, making it distinct from A1 through A sub 4. Consider xi, the 3 permutation, right? We're piling up Greek letters because we're fixing to do a transposition thing again. So we got xi and zeta. Xi is how that's pronounced commonly. Xi is the 3 cycle, A1, A3, and B. Zeta is the 3 cycle, A1, A3. I'm sorry, the product A1, A3, and A2, A4. This thing we had up here. We know zeta is in n. This is a 3 cycle, so it's in A sub n. All 3 cycles are even. So again, as in case 2, if we'll do the conjugation, that'll give us something in n. Zeta is also in n. If you'll compute what this element of n looks like, excuse me, I got stuck. Sorry. Okay, we left off here, technical difficulties. Let's compute what this thing is. It's a 3 cycle. So write out those elements. It produces a 3 cycle. Hey, if you got a normal subgroup of A sub n that contains a 3 cycle, lemma 12 tells you it is A sub n. So in all 5 cases, we've shown that if A sub n has a proper normal subgroup, has a non-trivial normal subgroup, then that subgroup must be A sub n, so that there are no proper normal subgroups of A sub n. Question is, did we get all the cases? Let's see. Like I said, I want to present this a little bit different. Let me shrink this and pull up an image. All right, so let's read through this. Sorry, the fonts are kind of small. I want to see if we covered everything with those 5 cases. So here's a little image that has a brief description of the cases. It was 3 cycles, cycles of length 4 or greater, 3 cycles and 2 cycles, 1 3 cycle and 2 cycles. What do we have up here? 2 3 cycles or something. Let's see if we covered all the possible cases for the permutations. All right, to see why at least one of case 1 through 5 has to hold in all possible situations, consider writing the elements of n as a disjoint product of cycles. That's been fundamental in everything we've done. Case 2, n contains an element sigma, which when written as a product of disjoint cycles has at least one of the cycles of length greater than or equal to 4. So we're dealing with a permutation which includes a cycle of length at least 4. Case 2 describes a situation in which there is a permutation, which is the product of disjoint cycles, at least one of which has length 4 or greater. So that covers a lot of turf. That just leaves us dealing with 3 cycles and cycles of length 3 or less. So if case 2 doesn't hold, all the elements of n can be written as a disjoint product of cycles of lengths 2 and 3. Case 5 covers the case when n contains only permutations consisting of no 3 cycles and only 2 cycles. Every element of n is the product of an even number of disjoint 2 cycles. Even wasn't an extra hypothesis. Remember, this is happening inside the alternating groups, which only contain even permutations. So if it's only 2 cycles, case 5 has it covered. Oops. Don't need that. Need this one to advance. Case 1 covers the case when n contains a permutation consisting of a single 3 cycle alone. That was really the lemma that we had, the lemma 16. Sorry, was it 6.11? Sorry, lemma 6.11. Case 4 covers the case when n contains a permutation consisting of a single 3 cycle and a bunch of 2 cycles. So case 1, only a 3 cycle. Case 4, a 3 cycle and a bunch of 2 cycles. And contains an element sigma, which is the product of 1 3 cycle and some 2 cycles. Case 3 covers the case where n contains a permutation consisting of 2 or more 3 cycles. 2 or more 3 cycles, and that's everything. So a cycle of length 4 or greater in the cyclic decomposition, case 2. A single 3 cycle, case 1. 2 3 cycles, two 3 cycles was handled down here, contains 2 3 cycles. Unique 3 cycle, 2 3 cycles down here. An element which is a product of 3 cycles and some 2 cycles, case 4. So the 3 cycles dominated the cases. It was case 1 when we had a single one, case 3 where we had 2, case 4 where we had, this is 2 or more, case 4 where we had 1 3 cycle and some 2 cycles. That only leaves only 2 cycles, and that was case 5. So the alternating group, A sub n, is simple if and only if n doesn't equal 4. Back to the notes. All right. Sorry for the inelegance of that. Well, that's a standard proof that A sub n is a simple group, except when n equals 4. Okay, let's wrap up this section with dihedral groups. We're approaching this from the angle that we've defined the symmetry groups. What we're looking at now is a subgroup of the symmetry groups generated by a set of elements. A set of 2 elements, that's why these are called dihedral groups. So a definition of the dihedral group, you encountered things that look like this, I'm sure in senior level algebra. You usually thought of the dihedral groups as symmetries of n-gons. Dihedral group D sub n was a symmetry on an n-gon, is how you would approach it. It's kind of cool because you can draw pictures. But our formal definition is subgroup of S sub n, taking n greater than or equal to 3 here, generated by these 2 elements. A cycle on the symbols 1 through n. 1 goes to 2, goes to 3, n wraps back around to 1. And kind of using 2 different notations in one setting here. And permutation B that fixes 1, maps 2 to n, 3 to n minus 1, blah, 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 and n to 2. It interchanges n and 2. It interchanges 3 and n minus 1. Somewhere in the middle, index I gets mapped to n plus 2 minus I. Plug in I equals 2 and you'll get this n. Plug in I equals n and you'll get that n. So what you're doing, this is the when you flip the n-gon. We're fixing this vertex of that regular n-gon and we're flipping things around. N and 2 are interchanged, 3 and n minus 1 are interchanged, and so forth. It can be written in this sense in terms of a product of transpositions, if you like. We're actually going to do a few little computations and we'll use this form. So is that a group? Yeah, it's a group. It's a group subgroup of S sub n generated by these two elements. It's called the dihedral group because it's generated by two elements. Geometrically, that corresponds to taking an n-gon and clicking it around, or taking an n-gon and flipping it around. So that's what A and B do if you want a geometric interpretation. Some discussion of that in one of the exercises. We'll look a few sections down the road at a way to define a group in terms of generators and relations which they satisfy. This next result, last one in the section, could be recycled as a presentation of a group. We're not quite there yet. What we have is a subgroup of S sub n. So we have a big umbrella group and we're just looking at a subgroup and dealing with it in terms of some properties of the two generators of that subgroup. So for each n greater than or equal to 3, the claim is the dihedral group D sub n is a group of order 2n whose generators A and B satisfy the conditions. A to the n is the identity, right, written in terms of a permutation here. B squared is the identity. B is its own inverse. A to the k doesn't equal the identity when you raise A to power k strictly between 0 and n. These first and third observations tells you A is an element of order n, by the way. So it gives you a cyclic subgroup of order n, in fact. And you have the relation BA equals A inverse B. This is how geometrically flipping followed by rotation is related to rotation followed by flipping. They're not commutative. Something happened here with a presence of an inverse element up there, which represents a rotation in the opposite direction. So the claim is dihedral group is order 2n and its generators satisfy these conditions. In addition, any group that's generated by two elements that satisfy these conditions is isomorphic to the dihedral group. So there's some uniqueness claim. This information uniquely determines the dihedral group. Okay, so let's look at a proof of that. This one a little bit computational too. Remember, A was the cycle of length n as given here. So certainly A to the n power is the identity. It will fix all of those elements. You take A to the k power, you won't get the identity if you choose that exponent to be anything strictly between 0 and n. You're familiar with behaviors of powers of cycles. B fixes 1. Remember, B mapped 1 to 1. So B squared fixes 1. Okay, so that's not quite the claim, but we do have B squared fixes 1. Let's check the other symbols. So take any symbol between 1 and n except for 1. B maps that symbol I to n plus 2 minus I. So what we had in terms of the representation of B in the definition of the dihedral group. So if we look at B squared of I, the symbol, it will first take B of I to n plus 2 minus I. That's what B does to the input. And now B will apply to that entry. So we'll get n plus 2 minus that entry. I mean, B takes an entry to n plus 2 minus the entry, unless you input 1. So we get first applying B to this symbol, n plus 2 minus I, and over the range, we're not getting a 1 here. And then this is mapped to n plus 2 minus I, cancellation, we get I. So B squared fixes 1. That's easy because B fixes 1. And B squared fixes I. B squared maps I to I for these symbols. In other words, B squared fixes all the symbols. B squared is the identity. And that's the conclusion here. So that takes care of part 1. We need this relationship between A and B. We're going to use this a few times. BA equals A inverse B. Something to note that will be necessary in the proof is this has the B on the left and the A on the right. This has the A on the left and the B on the right. Well, not exactly. It's not exactly commutativity, but here we are reversing the order in some sense. So that'll play a role. The fact that I can kind of move A's to the left and B's to the right in a certain sense. In that this lets me do some kind of manipulation like that. So first we need to establish this. So let's look at BA. Here's B, written in terms of the symbols 1 through n on the top and their images on the bottom. A, simply written in the cyclic notation. So I'm mixing notations. No big apology for that. It's the only way I could fit it on the slide, really. So it'll look reasonable. If you'll go through and perform the manipulations, let's maybe do one of those. Let's look at where I-1 is mapped. I-1, we'll read this times this, so this cycle we deal with first. I-1 in this is mapped to I itself. Then go to the other cycle, other permutation, and that takes I to symbol n plus 2 minus 1. So we started with I-1, we went through I to n plus 2 minus I. So in the product, I-1 is mapped to n plus 2 minus I. Now you can take all those values pertinent to I and produce the vast majority of this. Trust me on the product. We get something like this. This can also be written as the cycle in n minus 1 through 1. So actually, this is the inverse of this cycle. This is A inverse times B. And what we've shown or can show computationally is BA equals A inverse B. Yeah, because they both equal this thing here in the center of the slide. So we've got two holes. So the A and B elements, as given in the definition of dihedral group, satisfy the conditions put on them in property I and property II. Now, what we need to do is deal with the fact that they generate a group of order 2n. For that, we need to go back to theorem 1.2.8. Theorem 1.2.8, might pause and go look it up, tells you when I have a set of elements that generate a group, what the elements of the group look like in terms of those generators. If you only have two elements, A and B, then you get a power of A times a power of B times a power of A times a power of B, blah, blah, blah. Of those exponents, it could be zeros, so maybe it starts with a power of B and not a power of A. You don't have commutativity, so you're stuck with this alternating AB powers stuff. And the exponents, they could be any integer. So we could have inverses in here. But remember, BA equals A inverse B. Let's go back to the previous slide. BA equals A inverse B. This lets me move A's on the right to the left. Okay, I pick up some negatives, exponents, if you will, when I do that, but it lets me move the A's to the left. So what we can do when we have a product like this, I can take, if you want to do it slowly, one of these B's and one of these A's and interchange them. One of these B's and that one A and interchange them. I can slowly walk the A's over to the left and the B's towards the right. As you do so, exponents will change, but you can get the A's on the left and the B's on the right. We'll have some power of A times some power of B. That identity lets us do that kind of movement of A's and B's. You don't have commutativity, but you got a relationship that lets you move the powers of A to the left and the powers of B to the right. So property 2 allows us to do that. We've done that kind of thing a few times before. Now remember, A was an element of order n, was a cycle of length n. So it only produces n different things. Raise it to the n power and you get the identity. So the powers of A, we may as well restrict the exponent to be 0 through n. After all, it cycles around to the identity every n times. B was an element of order 2. Remember, geometrically, it was a flip of an n-gon. It's its own inverse, so square it, get the identity. So the exponent on the B, we can take to be 0 and 1. You want to take 1 and 2, that's fine, because 2 is going to yield the same behavior as 0. n is going to yield the same behavior as 0 for the A element. This is an element of order n. This is an element of order 2. So that allows us to say you can use these exponents instead of having to let I and j range over all the integers. Part 1 told you that the order of the elements was as claimed. So let I be anything between 0 and n. What we're doing here is trying to show the order of the group is 2n. There it is at the bottom of the slide. I want to show when I use different i's and j's, these produce different elements. So what we're doing is looking at how these things behave on particular symbols. Remember, ultimately, we're dealing with permutations from S sub n. So they're permutations on the symbols 1 through n. So take I to be between 0 and n as given, excluding the n, and take j to be 0. A to the I, b to the j, what does that do to the symbol 1? J is 0, so b to the j is the identity, so that just gives out the identity. What does a to the I power do to the symbol 1? Remember, it was a cycle. It cycles it around I times to produce the symbol 1 plus I. If we look at A to the I, B to the J applied to 2, when J is 0, still in that setting, when J is 0, B to the 0 of 2 just leaves us with a symbol 2. A to the I, we'll click it around and produce 2 plus I, reducing mod n if necessary on some of this. So that gives us symbols 1 plus I, 2 plus I when applied to 1 and 2 respectively when j equals 0. What about when j equals 1? They'll do something different. For 0 in the appropriate range and j equals 1, now we're dealing with permutation B, a little more hands-on. A to the I, B to the j, what does that do to 1? Well, remember, B to the 1 power, it fixed 1. It was the folding around the vertex. That would be the vertex labeled 1 and the regular n gone, and 1 was fixed by B. So that gives us A to the I of 1 and gives us a 1 plus I. A to the I, B to the j of 2. Okay, this one's a little more complicated. That would be A to the I, B of 2, j equals 1. The permutation mapped 2 to n. Remember, permutation B mapped 2 to n. Look at the definition on the previous slide if necessary. Actually, let's do that. B mapped 2 to n. Yeah, B mapped 2 to n. Here's B. So that gives us A to the I to the A to the I of n. I is simply added on to n and the label reduced mod n as needed. So we're getting different behaviors here. If I doesn't equal I prime, so if we have different exponents on the A, look at A to the I, B to the j versus A to the I prime, B to the j. What we're going to get out for A to the I, B to the j of 1 is 1 plus I. Right, we got 1 plus I out based on, actually only on the A, so we get the 1 plus I out. If we replaced that exponent with I prime, we get 1 plus I prime out. 1 plus I doesn't equal 1 plus I prime. So if you have a different exponent on the A's, we're getting a different permutation because it treats 1 differently. This permutation applied to 1 doesn't equal this permutation applied to 1. The difference in these permutations is the exponent on the A. If the J's are different, okay, there's only 2 possible values for the J's. Say J equals 0 and J prime equals 1. Primes just for difference. If we look at A to the I, B to the J, what it does to 2. We saw that 2 was mapped to 2 plus I down here. If we'll apply what we get with an exponent of 1 on B, which is what we did down here, we see that 2 is mapped to n plus I. And 2 plus I doesn't equal n plus I. If you look back at the statement, we're looking at dihedral groups where n is greater than or equal to 3. So we don't have an equality there either. And what that amounts to is if either the exponent on A is different or the exponent on B is different, then A to the I, B to the J is not the same permutation as A to the I prime, B to the J prime. So as I ranges over these n possible values and J ranges over these 2 possible values, those permutations are different. Actually, they're either different on 1 or on 2. So it was easy to show a difference. So how many of these permutations are there? N times 2, there's 2n of them. So we're dealing with 2n permutations. They're distinct. That's what this stuff here was all about. So we haven't counted the same one twice or anything. And so knowing that D sub n consists of all such elements of that form, and we've shown there's 2n of those elements, we know the cardinality of D sub n equals 2n. So we've got the conditions 1 and 2 satisfied by the generators, and we've got the dihedral group of the correct cardinality, correct order. All right, there was an isomorphism claim as well. It's got a couple pages left here, I think. Suppose G is a group generated by A and B, where A and B satisfy 1 and 2, and that group is of order greater than or equal to 3. We want to show that's the same, that's isomorphic to the dihedral group. So we'll define a homomorphism ultimately. Theorem 1.28, and the argument we just had works in this setting. We've assumed the same hypotheses on the symbols A and B, so we can still draw the conclusion that elements of this group G are of the form A to the I, B to the J, with the appropriate choices as before of the I's and the J's. So we're going to have to map from the dihedral group into this group G. Let me denote the generators of the dihedral group as subscripted A's and B's, denote them as A1, B1. Here we're assuming A and B are the generators of G. So let me take the generators of D sub n something different. So split subscripts on them just to distinguish. Then define a mapping from D sub n to this mystery group G as mapping f of A1 to the I, B1 to the J, map it to A to the I, B to the J. That includes all the elements of the dihedral group? Right. We saw on the previous slide that in the dihedral group, we get powers of A and B, where the exponents were between 0 and n for the I, and J was either 0 or 1. So yeah, this includes all the elements of D sub n. I suspect this includes all the elements of G, but we'll deal with on-to-ness here in a little while. That's the mapping. We want to show it's a homomorphism. So let's take 2 elements of D sub n. All right, 2 elements of D sub n are of the form A sub I to some power, A sub 1 to some power I, B sub 1 to some power J. These restrictions on I and J. So there's the first element of D sub n. Take a second element. All right, second element, same generators, different exponents. So f of first element of D sub n times second element of D sub n. You know, hey, we got A1s and B1s. We saw we can move the A1s to the left and produce a product of A's times a product of B's. As you move these things to the left, we're picking up negative signs on the exponent. So we end up with an A sub 1 to the I minus I prime. The B's just move smoothly to the right. And we had the inverses that popped up with the A's. So on the right, we get B sub 1 to the J plus J prime. Right, just add exponents on those, some complications with inverses as you move the A's. And we end up with the product expressed in this form using that second property. What does F do to a product of A1s times a product of B1s? Simply produces A's and B's with the same exponents. So this will produce unsubscripted A and unsubscripted B We're over in group G now, right? F took us from the dihedral group to group G. So this gives us elements of group G. Hey, these satisfy that same BA equals A inverse B thing that allowed us to swap the orders. So swap them back. So do the same thing you did previously. We put the A's on the left and the B's on the right to get this. Well, split them back up in such a way that you get the corresponding exponents. Same idea backwards. Hey, A sub I, or A to the I power, B to the J power, that's F of A1 to the I power, B1 to the J power. And similarly with the primes. So this becomes F of A1 to the I, B1 to the J, F of A1 to the I prime, B1 to the J prime. Remember, we started with a product of two elements written in the form that we know the elements of D sub n can be expressed. F of that product is the product of those F's, is a homomorphism. That's exactly what we need to show we have a homomorphism. Oh, with the added little caveat that, yeah, this is what the elements in the dihedral group look like. We know that. We established that previously. So we do have a homomorphism. We want to show we have an isomorphism. You know, every element of G is of the form A to the I, B to the J, same argument that we used in the dihedral group. So this mapping is in fact onto. So we have an onto homomorphism. We have a surjective homomorphism. That is, we have an epimorphism. We want an isomorphism. So as morphisms go, we're 2/3 of the way there. We got the homomorphism. We've got the surjectivity, the onto. We just need the one-to-oneness. So it's missing the one-to-oneness. So let's show that mapping is 1-to-1. How would you like to show that mapping is 1-to-1? 1-to-1 homomorphism. Ooh, let's look at its kernel, as we've commonly done. So that's how it'll finish up. We show F is 1-to-1. And so we'll have 1-to-1 onto, we'll have a bijection. It's a homomorphism. We will have an isomorphism. Theorem 1.2.3 part 1 says if the kernel consists only of the identity element, then we have a 1-to-1 mapping. Then we have a injective mapping. So suppose we take something in the kernel, the things in the kernel, right? We're mapping D sub n into G. This is what the things in D sub n look like since we threw the subscripts on the generators. So we've got an A sub 1 to the I, B sub 1 to the J with the usual constraints on the I's and the J's. Let that be something in the kernel. We're going to show that something is actually the identity. And so the kernel consists only of the identity. So we'll have a 1-to-1 permutation. I'm sorry, a 1-to-1 homomorphism that's also onto, and we'll have an isomorphism. So take this to be in the kernel. What does F do to these things? It maps them to A to the I, B to the J's. It drops the subscripts. Being in the kernel means this thing must equal the identity. So saying we have an element of the kernel ultimately means we have this kind of relationship between the A's and the B's. Assume J equals 1. In this representation here, if we assume J equals 1, then we've got A to the I times B equals the identity. So it must be the inverse of B is A to the I. From that little equation there, getting the identity. Now doing manipulations in group G, not in the dihedral group. So that'll give us that relationship. B by property 1 up here applied to the group G. B is an element of order 2, so it's its own inverse. So B inverse and B are the same. So we've got this little equation under that assumption. Part 2 tells us A to the I plus 1, that is A to the I, A equals, well, we just showed A to the I is B, so substitute for the A to the I, this parameter B. That becomes B times A. Part 2 tells us B times A is A inverse B, giving us this. Remember, B equals A to the I, as we just showed in this case. Change the B back into an A to the I. That gives us an A to the I minus 1. If you've got A to the I plus 1 equals A to the I minus 1, easy enough to manipulate those powers of A, and you learn that A squared equals the identity. A squared can't be the identity. Remember, A to the N is the identity, and for nothing smaller than N except for 0 do you get the identity out from a power of A. Remember, N was greater than or equal to 3, so we can't have N equals 2 in this. That's a contradiction. So that contradicts this little piece of part 1. So we can't have J equals 1. In the manipulations up there, we must have J equals 0. If we have J equals 0, then this little relationship right here, A to the I, B to the J equals E, becomes E equals A to the I, B to the J, B to the 0. This is the identity. So the identity equals A to the I. But then we had I between 0 and N, excluding N. You can't get A to the I equal to the identity for any of these values of an exponent. That exponent must be 0. Notice a slight difference down here. We've got 0 less than or equal to I. When we chose the i's, it's a different statement here. So it must be I equals 0. So we just showed J is 0 and I is 0 if this occurs. So it must be that I and J are 0. We chose this element of the dihedral group, A sub 1 to the I, B sub 1 to the J. That thing must be A sub 1 to the 0, B sub 1 to the 0. Must be the identity in the dihedral group. So the kernel of F consists simply of the identity element of the dihedral group. The kernel of F consists only of the identity. Theorem 1.2.3 part 1 tells you that's a one-to-one mapping. We had onto and homomorphism from the previous slide. Now we've got one-to-one. You've got a bijection that's a homomorphism. That's what an isomorphism is, and that's a uniqueness. So any group G satisfying 1 and 2 has to be isomorphic to the dihedral group. So in other words, go back to the notes because they're there. If you have a group generated by 2 elements that satisfy these conditions, that group is isomorphic to the dihedral group. So these 2 generators and these equations relating those generators to each other, they uniquely determine the dihedral group. That's an example of a group presentation, as we'll see later on. It's kind of why we're doing this now. But that gets us through symmetry groups, alternating groups, and dihedral groups. So there's a little class of 3 little classes of finite groups, and they're all related to the symmetry groups, right? The alternating groups were subgroups of the symmetry groups. The dihedral groups, it turns out, were subgroups of the symmetry groups as well. There's something really, really fundamental about groups of permutations. Like every group is isomorphic to a group of permutations, we'll say at some point later on. And this allows for infinite permutations as well. All the permutation of an infinite set is is a bijection of that infinite set to itself. So that takes care of 1.6. So let's call it a day. I'll see you in the next section here in the next video. Have a nice day.